Hello and welcome to Algebra 2 tutorial. In this video, we're continuing our look at compound interest. And one of the things we did in our last video is look at what happens if you do compounded interest at different rates, yearly, monthly, or daily. In this video, we're going to take a look at what happens if you charge interest faster and faster. So even faster than monthly and daily, more and more quickly. So until we get to what's the limiting value if you continuously compounded interest, so that's you do it an infinite number of times. So we're going to find that limit first, then we'll have ourselves a new equation, and I'll give you a good example of how to do that before I give you some practice problems. So first, let's find the limit of continuously compounded interest. So here we're just going to sort of go down the line here and calculate compounded interest at different rates. So the only thing we're going to change is how fast we are compounding it. So we're going to do it yearly and then monthly and then daily. That's where we stopped last time. And we're going to go even further. What if interest was calculated every hour or every second? I'm going to guess secondly might be a word. Probably not. All right, and for this we need some numbers, so we're going to start with $2,000. Our APR is 12%, and we're going to do for 5 years. So all those numbers are going to remain the same for all of these examples, except for the end value, how fast we are compounding interest. So the first one is nice and easy. Y is equal to A, which is 2,000. Our B is 1 plus our interest rate, so that's 1.12 to the power of x, which in this case, that's 5. So we just need to type that into the calculator. Make it a little bit darker here. So it is 2,000 times 1.12 raised to the power of 5. And so I'm going to put it down here, 3,524 and 68 cents. All right, now monthly. So monthly, we have to use our compound interest formula, which is A is equal to 2,000, 1 plus the interest rate divided by how many times we're compounding it, which is going to be 12 because there's 12 months in a year, and then 12 times the 5 years. So we're going to type that into our calculator now. Now remember, when you raise this to the power, you want to put that in parentheses, 12 times 5. Hit enter. And our amount is 3,633 and 39 cents. So you can see it definitely got bigger. 3,500 up to 3,600 now. So as we're compounding more often, it certainly looks like we're getting more and more expensive here. All right, now let's try daily. So again, it's 2,000. That's not changing. 1 plus, oops, that shouldn't be where the plus is. 0.12 divided by, so if we're doing this daily, it's no longer going to be 12. It's going to be 365 to the power of 5 times, oops, probably shouldn't start with the 5. 365 times 5. So let's type that in, 2,000, 1 plus 0.12. So now the n changes to 365 raised to the power 365. So you can see that this did get bigger, but not by nearly as much as the last jump we did. Let's call that 88 cents. So we went from 36.33 to now 36.43. So that's only what, $11, $10 difference? So we're still getting bigger, but we didn't have nearly as big of a jump. All right, so now let's take a look at hourly. So I need a different color here. So A is equal to 2,000. 1 plus 0.12. Now, what is the end value? How many hours are in a year? Well, I need to do that because I don't know. So there are 24 hours in a day, and there's 365 days in a year. So our n is now 8,760, and up here we have 8,760 times 5. You might think, holy mackerel, this is going to be crazy. It's actually not going to be that bad. So watch, 2,000 times 1 plus 0.12. Oops, didn't hit the plus there. Plus 0.1. Not sure why that's not clicking. 1, 2 divided by 8,760 raised to the power of 8,760 times 5. So we get 3,644 and 22 cents. All right, as you can see, we did go up a little bit, but we went up by almost nothing. We're at $43 here. Now we're barely at 44 when we're getting interest every hour. And if you did seconds, you'd realize it would go up, but it would go up by even less. And so while, yes, we are getting more and more expensive here, I guess you could say, but we're getting more expensive by less and less. And so I'm guessing this $3,644 wouldn't actually change by much at all. Maybe get to 45, but not more than that. There is a limiting value if you went to seconds and even past that. And so we do go past that to what we call infinitely compounded interest or continuously compounded interest, which is an infinite amount of interest. And yes, it gets more expensive, but there is a limit. And for that limiting value, we have a new equation. This will give you the most possible amount of money you would get from compounding interest more and more frequently. So here it is. We got some familiar letters and we got a new letter. So A is the same. That's still the amount. P, that's also the same. That is still your principal. That is what you start with. R, that is still your rate as a percent. And T is still time. That is in years. And we have our last variable, E. That is just a number. It doesn't change. It's a special number like pi. I'm going to put similar to pi. Now pi is a number, 3.14159, and it goes on and on. Instead of writing the decimal, we just write pi. E is also a number that goes on forever, and instead of writing that number, we just write the letter E because it's easier. I guess you could sort of think of that way. Let me show you what it is. It is actually on your calculator. And because it's an exponential, it almost always has a power. It's right here. It is already e to the power of x because the calculator knows you're probably going to raise it to the power of something. But if we want to know what the actual number is, just raise it to the power of 1. And it is the number 2.718281828, and it keeps going. It doesn't keep repeating, but it does keep going. And so E is just a number. It's actually not a variable, just a special number kind of like pi. So Using that formula, we can now calculate continuously compounded interest. So let me show you an example to kind of show you this is not actually that hard. So here's our scenario. A bank has thought of a crafty way to attract customers. They are offering continuously compounded interest of 4% with their savings accounts. How much money would you have after 2 years if your initial investment was 500? So I'm just going to plug all this in. The amount is equal to the principal, e to the power of the rate, which is 0.04%, times the time, which is 2 years. So you can see that's pretty easy. And then we just got to plug that into the calculator and see what we get. So 500 times e, so second e down here, to the 0.04 times 2. And we get our answer there of $541.64. That is the most you could get if you continuously compounded interest. So the bank think that's a pretty good idea because it will attract customers. But is that really that much more if you compounded monthly? Let's check that with what we've done in the past. So here's our long compound interest formula. 1 plus the rate, which is 0.04. And if we're compounding monthly, that is a 12. And to the power of 12 times our 2 years. Is that really going to be that much different? Well, let's see. So 500 times 1 plus 0.04 divided by 12 raised to the power, I'm going to do that part in my head, 12 times 2 is 24. So $541.57. So you can see that that is almost no difference at all. Yes, this is a few cents more, 7 cents, but almost nothing. So that is not actually a very good way to attract customers if they know what they're talking about, because there's almost no difference between compounding monthly and compounding continuously with that problem. All right, so that is continuously compounded interest. Yeah, the limit process was kind of long and hard, but the actual new equation you're using is pretty easy, and it doesn't usually make that much of a difference. So here's one for you to try. Make sure you can do all 3 methods, yearly, monthly, and continuously on this problem. Good luck.